Welcome, Pushkar.
Hey everyone, how's it going?
Good.
All right, let's get started. Let me share my screen. All right, let's get started. Hi everyone, my name is Pushkar Garg. I work as a staff machine learning platform engineer at Clari, and excited to be presenting this topic, which is a slightly niche area, but like more focused in terms of like if you talk about data quality. But I'm going to talk about data capture on model endpoints and how that helps in running data observability on like the models deployed in production. So let's get started. So the agenda for today in my talk is going to be, so we'll go over the different data components that you may see in a data platform which powers all of the model building capabilities in the AI and ML platform. Then we'll go over the importance of monitoring data quality, and then in general model monitoring as well. Um, uh, uh, After that, we'll move on to like how do we actually measure data quality with metrics. What are the metrics that we need? How do we build that infrastructure to identify and capture those metrics? The next topic we're going to cover is on the managed data capture. So there are certain tools which if we use to deploy our models, they provide managed data capture, meaning like automatic data capture, and what are some of the limitations related to that, and then what may be the need for a custom data capture architecture, and then how do we go about implementing that. And then it will all we try to bring all of that together into like how does that fit it into the downstream systems, and then some of the best practices and some lessons learned around like implementing custom data capture. So let's start with the different data components, right? As any company would already have in production their production databases, right? And then with the advent of generative AI nowadays, we are seeing a lot of the use cases for utilizing the data which is stored in silos in like S3 buckets or like object storage, which can be like files, call transcripts, email bodies, anything like that, right? So how do we bring all of that data together into one component which can be used to run transformations, and then ultimately build features, so that we can use those features to ultimately build models. So in this diagram, I've tried to like separate out the data world and then the ML world, so that it becomes easier to specify responsibilities and also implement like data quality checks. So in this case, it's almost possible to implement data quality checks at all of the checkpoints wherever data is flowing and ultimately getting persisted. So we start with the production databases, and then the object storage, to bring together the structured and unstructured data into the data lake, for example. And then following the medallion architecture that has been popularized by Databricks, we can transform that data over certain schemas, and then move from like a bronze to silver to gold schema, which gives you like the confidence that that this data will always be ready for like consuming into like model building. So once that data has been transformed into the modeled layer or the gold layer, you can sync that into an offline feature store, and use that to train the models. So run training jobs on the offline feature store, develop models, and then ultimately deploy those to a serving endpoint, which serves prediction requests from upstream services. So, like any kind of model prediction that can be done, once the model is deployed to that serving endpoint, it can take care of that. And there may well also be a need to query real-time features from an online feature store, which ingests real-time features from upstream services that may or may not go through transformation. So like your real-time services may be creating data for a particular user that you want to do a prediction for. So it's necessary to get the most updated data that may go through transformation. So ultimately, all that comes together in the online feature store, and then the serving endpoint can use that to get the latest data about a user and or any product, and then make a prediction. So the focus of the talk today will be on the serving endpoint, like on like the data quality on the serving endpoint, and how do we enable that by enabling data capture in the first place. So yeah, excited about that. So the importance of monitoring, like as all of you already know, right? Models prediction quality is as good as the data quality, right? So garbage in, garbage out, whatever is fed to the model is comparable to the prediction that is generated by the model. So the other importance of monitoring in general and data quality in more, to be more specific, is to identify training serving skew. When we train the model on a certain data set, it identifies the relationship between the independent variables and the dependent variable, and then it attaches a certain weight to all of those variables to come up with a certain equation, and then ultimately give you, for a certain set of features, using those weights, give you the output, which is the dependent variable. Now if the data in production is much different, right? If the distribution of the data in production is much different than it was in training, you can expect there needs to be some adjustment to the weights that needs to be done for an accurate prediction. So to be able to identify that that has happened in the production data, meaning that there has been a distribution drift in the inference data, we need to be able to capture data and then ultimately identify that and then retrain the models on the latest updated data to capture those changes. The next type of identification that we need to do is concept drift. So the data in itself may not have a large distribution change, but the relationship between the data and the dependent, like the features and the dependent variable, may change over time due to, like, for example, COVID, right? So when COVID happened, a lot of the models which were in production would not have performed up to the mark because the overall situation has changed, and then the relationship between the features and the prediction has changed. So it's necessary. Monitoring is necessary for identifying that use case as well. And then finally, like I said, the data quality checks can be implemented at all checkpoints of a data pipeline, but but on the serving endpoint is sort of the last frontier where you can still identify issues in the data pipeline. So anything which may have been ignored or which may not have been captured in terms of failures or in terms of having breakages in the data pipeline can ultimately be identified in the serving endpoint if you decide to have monitoring there. So we've established the importance of data quality. Now let's see how do we measure data quality, right? So there are different types of metrics, and these are not the exhaustive list of metrics, but this is something that is this is something that can be easily enabled on a serving endpoint to identify the usual data quality metrics. So let's start with the data type check, right? So data type. So in here, what we're trying to do is we're trying to take the training data and compare it with the inference data to identify um, these checks. So what we are doing is we're looking at every column in the training data, comparing it with the corresponding column in the inference data, and then identifying these. So data type check is has each column, if each column has the same data type as it was present in the training data. Completeness check, how many nulls are there as compared to the training data, right? So if you're getting more nulls as part of your inference data set, that it means that there is some kind of broken, either like there is a broken pipeline, or there has been some change which has not been accounted for, and then this issue needs to be fixed. So to be able to identify that that is happening is the first frontier, and then move on from there, to rectify it is the next. And then I think the most important one is like the baseline drift check. So how do we measure that there has been a distribution change, right? So to be able to measure that, we look at each column and then compare the distribution of the data in the training data set to the inference data set, to see if there has been a distribution change in the data, and trigger some alerts if there has been like a significant change. Now there are built-in algorithms that can be used. It's actually non-trivial to implement it, if you go the native way, right? If you try to implement it using an algorithm, but there are like libraries like DQ which support identifying the drift in the data by just using the library directly, and supplying it with like the two columns to compare. So this is something that can be used, and it's a good metric to identify. And then these last two are straightforward. Like if there is any missing column in itself, or if there is like any extra column that you did not expect in the inference data, then that needs to be identified and rectified as well. Okay, so once we have established how do we measure data quality, by generating the metrics, right? Now, how do we generate those metrics? So let's start with the training data here. So you have a training data set, you run a training job, build a model, deploy the model to an endpoint, and then that model endpoint serves prediction requests from the prediction service. um, to be able to generate those metrics, we need the training data and we need the inference data. So that can the inference, so we already have the training data, and we can use data capture to capture the requests that are coming into the model endpoint, to create that inference data set. Once both of these are available, we can pass them on to a monitoring job, and that monitoring job can look at each column in the training data and inference data, and then generate the metrics that we just discussed, and then persist them to your choice of observability tool. Yeah, it's important to version training data, because a model goes through like multiple experiments, multiple A/B testing. So it's necessary to capture the current version of the model was deployed with which version of the training data in a model registry, and then the monitoring job can pull that data from the that model registry, and then load that from S3. And then it is also possible to generate like first-hand baseline and constraints using that training data, and then only use those constraints to look at the inference data, and then for each column, right? Let's say, what is the range bound of the variables of the features that you see for a particular column? What was that compared to that training data set? So it's possible to optimize it even further, but this is like an abstraction on that front. Okay, so now let's talk about data capture, right? So we identified that we can enable data capture on a model endpoint, and then that can help us in capturing the inference data. So there are automatic ways of capturing data. So for example, if you deploy a SageMaker endpoint, your model code gets deployed on an EC2 instance, and it would automatically provide you a server, a Flask server, which is the which uh, gets all of the prediction requests in HTTP or gRPC, whatever you have it, and it will forward the request to the model. Model will make what model will use those features to make the prediction. It may also query the online feature store like we discussed, and then it will make the prediction, return the request to the server, and then the server will persist the combination of the features and the prediction, so as it received from the prediction service and the model. So So imagine if you're using protobuf as the object in the request to the server. So the server will persist that, and then the model will deserialize those requests to make the features in plain text. It will generate the prediction, serialize the request again, and then send it back to the server to send it back to the prediction service. So in here, the server will capture the requests in protobuf format if that is the case. So that's how the managed data capture works. Now, what is the need for coding custom data capture, right? So first of all, it doesn't work for real-time features in this particular case, for example, with SageMaker. So whatever is sent to the server, that's what is captured in like the inference data set for data capture, if we go like the managed way. So imagine the prediction service sending just a user ID to the server, and then the model querying the online feature store for the latest values or the latest features related to that particular user. It would not capture those requests or those features that the model got from the online feature store. And then it will just persist that user ID and then the corresponding prediction. So there are ways to still like recreate that data set by doing time travel queries. So ultimately what happens is whatever is the data that comes in the online feature store gets synced in the offline feature store at a specified cadence. So what you can do is you can run uh, another job which parses all of the data in the data capture logs, and takes the request time and then regenerates the set of features from the offline feature store by doing time travel queries, that whatever is the feature set that the model would have used at that time to make the prediction, you can recreate that data set and then run the monitoring job to have like the full set of features to compare against the training data. And one thing that I identified was that it does not work for multi-prediction models. So, like, what I mean by multi-prediction model is, like, for example, a ranking model where you would have to predict a set of requests. It's not a multi-model endpoint per se, but it's one model, but it is serving multiple requests. So, like ranking, for example, you would have multiple items that you would want to rank, and then generate a score for all of them and then rank them in order of user interactivity or whatever. So in that case, the persistence to S3 for the data capture would involve like a whole array of objects, and then it at that time SageMaker was not able to handle that. So there was this another need there. And then, like I discussed earlier as well, if you're using protobuf as your request object, you need to keep track of the serialization and deserialization class to be able to deserialize the requests that are captured in S3 from whenever you run the monitoring job to get the data in plain text. So these are some of the limitations because of which we implemented custom data capture. Excuse me. Now let's look at custom data capture, right? So how did we go about implementing custom data capture? So the uh, you can implement a data capture buffer on the model itself. So it will use the hardware of the model endpoint that it is running on, like in terms of memory and compute. But you can still code that within the model code. So what we did was we created a package, and that package has to be imported by any data scientist who is looking to implement this data capture. And what can be done is you instantiate that buffer, and then you after the model has made the prediction, right? So let's say it queried something from the online feature store, it made that prediction, and then ultimately it's able to get everything in plain text. And then just before serializing the request to send back to the server, it can capture all of that data. It can append that data to the buffer that it instantiated. So, and then the buffer from time to time, what it will do is it will flush it out to S3 based on different knobs that you would want to enable, right? So what we did was like buffer memory size, message count, and then the active buffer time. So let's say from after every 5 minutes, we would persist the data to S3. So this is something that we did for implementing custom data capture. And then let's go to like how do downstream systems use this. So like we discussed, training data, and then the inference data. So the inference data is generated by the data capture. Monitoring job takes both of these as input, generates the metrics, pushes the metrics to your observability tool, and then you can set thresholds for these metrics to go. If they go over a certain value, you would send alerts, and then those alerts go to a notification queue, and then that notification queue can have subscribers downstream, which on notification send an alert to PagerDuty or Slack, and then retraining can be done basically too. So that sort of completes the loop on observability. So you started with data capture, identified, created the metrics, identified if there is anything wrong in the model, and then completed the loop with retraining. And then this data capture can also be used for running model quality, right? So you can imagine that the inference data can be augmented with the ground truth, and then ultimately that data can be joined with the data captured in production. So the monitoring job will have the input of, for this set of features, what was the prediction that the model did, and then what was the actual ground truth, and use those to compare, and then generate model quality monitoring metrics as well. So this is how data capture overall comes together and then creates the foundation of running observability, or ML observability in particular. So some of the lessons learned around implementing custom data capture is like batching requests is obviously a very good idea. You would not want to persist every request that you get to S3, because that hampers your IO performance. Experimenting with different knobs to find the right threshold is a good idea, like we discussed. Memory size, the total time after which the buffer would write data to S3, or the message count, whatever may work for you. But integrating those knobs into the code is a good idea. Sampling of requests is something that you can save money on. Maybe not a lot, but like in terms of compute, it there can be some savings, right? So if there is not a need to capture everything. So in our case, like 75% of the requests are also able to identify if there is any kind of data drift. And then performance benchmarking is also important, because this is something that is running on the endpoint itself. So it's important to be able to set some SLA around how much latency this data capture buffer may add. So it's important to do benchmarking to identify like the average, max, and 99 percentile latency that may be added as part of the data capture buffer. Yeah, that's my time, I think. Thank you very much for listening in. Happy to answer any questions if there are.
Awesome. Thank you so much.